so yesterday we learned how to calculate probability. You guys remember that? What was the formula? It was favorable over total, right? Favorable over total. And the problem would give me enough information to where I could find the total, right? Well, today, with these examples, I don't have that information. I don't have a total. So I have to now use either tree diagrams, or we're going to learn another method called the counting principle to find the total number, and then I can calculate probability. Do you see the connection to yesterday's lesson? Yesterday they gave me the total. Today I don't have the total. I have to calculate it, and then I can find probability. All right, so with tree diagrams, I want you to go ahead and turn in your books and follow along with me. So turn in your books to page 639. Page 639. All right, so on page 639 it says on the top there's a fruit smoothie example. All right, it says you're ordering a fruit smoothie. You have a choice of small, medium, and large, and you can include one of the following fruits: strawberries, bananas, or oranges. How many different choices of smoothies do you have? So tree diagrams, and that was not, we're going to answer that by doing a tree diagram, can help you find the total possible outcomes of an event using branches. Okay? So each branch of the diagram represents one set of possible outcomes. So the first branch is going to be our sizes of smoothies. The second branch is going to be our fruit choices. And then the third branch is going to be the actual combination that can come from the size and the fruit put together. All right, so what sizes were possible? Small, medium, and large. So what were my fruit options? Strawberry, banana, and orange. So I could get, for a small, I could get strawberry, banana, or orange. For a medium, I can get strawberry, banana, or orange. And guess what? Same goes for the large. So for all three of these size options, I have 3 fruit choices. All right, so then over in the combinations column, I can get a small strawberry. I could get a small banana or a small orange. Do you see how I'm listing them? So go ahead and finish the rest of the tree diagram. Okay, so again, we're just bridging them across: medium strawberry, medium banana, medium orange, and same with large. All right, and then once I'm done listing them all, how many combinations do I have? 9 combinations. That's my answer. You see it boxed down here in the bottom right-hand corner. So I do all that work to find the total number of combinations. So now I can take that number and I can calculate probability. For example, what is the probability that I will choose a small beverage, size small? Well, how many options are smalls? 3 out of 9. So put it in your calculator, 3 out of 9, and change that to a percentage, and what do you get? 33%. So there's a 33% chance that I could select a size small. You see how we calculated probability? We did all that work to find the total, and now we could play probability scenarios all day off of this example. All right, let's look at another example. Turn in your books to the next page, which would be the science camp. No, I'm sorry. We're going to do the number 1. Your turn now, page 639. All right, this is a movie theater example. The popcorn comes in regular, large, and jumbo sizes. You have your choice of plain or buttered popcorn. How many choices of popcorn do you have? So go ahead now and break it up into your categories. Again, each branch of the tree diagram represents one set of outcomes. So the regular, large, and jumbo, that's one set. And then plain or buttered, that's another set. So go ahead and set up your tree diagrams. First branch is size. Second branch is the topping or whatever, the choices, yeah. However you want to label it, that's fine. And then the third, obviously, is our combination. So regular, large, and jumbo. And what are the topping options? Plain and buttered for each size. Plain and buttered. All right, and now I just bridge them over. Regular to plain, regular to buttered, so I can have large plain, large buttered, jumbo plain, jumbo buttered, and I just start writing them in. Regular plain, regular buttered, and I finish it off. Okay, so once we fill them all in, large plain and buttered, jumbo plain and buttered, how many combinations? 6 combinations. So what is the probability that I would choose a plain option for my topping? How many plain options are there? There are 3 out of 6, which is 50%. 50%. All right, you see how we calculate that? Favorable over total, but we had to do this to figure out how many total options there were. The problem didn't give that to me. One more tree diagram. In this tree diagram, it's a science camp example, and it says you're attending 2 sessions at a science camp. Each session is assigned a color. Okay? Red, green, blue, or yellow. But whatever color you go to the first time, you won't go to the second time. All right? So my first category is the first session. Then I have my second session, and then the total combination. All right? Well, remember, they're broken up by color. So first session is red. And we're going to use R for red just to kind of abbreviate these. So if I go to red in the first session, what 3 options are there for my second session? Green, blue, and yellow. Because it's got to be the other colors. So then if my first session is green, what would my other 3 options be? Okay, now I want you to fill in the other 2 colors. For blue and yellow, what would my options be for the second session? All right, so blue and then yellow. All right, and what I'm doing here is I'm just starting to match them up now. Again, I'm bridging them across. So red and green, red and blue, red and yellow are possible combinations, and I'm going to just continue down the list and match up my combinations. And what am I doing here? I'm doing all of this so I can calculate how many total combinations there are possible. So I fill in the rest of my combinations, and I can see that I have 12 possible combinations. 12 possible combinations. Any questions, guys? So that's tree diagrams. That's tree diagrams. Now, there's another way that I can calculate the total number of outcomes without doing a tree diagram. Let's go back. Let's go back to the first example. In this first example, how many options were in the first category?
3.
How many options of fruit were there?
3.
What's 3 times 3?
9.
9. In the second slide, how many size options were there? 2. And how many topping options? I'm sorry, there are 3 size options, and how many toppings? 2. What's 3 times 2?
6.
And 6 was my total. In the third example, how many options were there for my first session? 4. And how many options did I have left for my second?
3.
3. And what's 4 times 3? 12. We call that method the counting principle. You say, well, why in the world did you just waste all my time with the tree diagrams if it's literally just a matter of I can multiply however many possibilities there are and find my total? Well, there's a couple reasons behind it. One is tree diagrams actually show you the how or the why behind that final number. If I were to just teach you the counting principle to start with, you wouldn't understand how you really got to 12. But now that you're looking at a tree diagram, you can see the breakdown. Would you agree? You can see the breakdown. Now, here's another reason, though, that we're going to kind of tend to lean towards the counting principle. What if you were to calculate a total outcome and it was 216? You want to do a tree diagram for that? Ooh, man, that would be massive tree diagrams. So tree diagrams really are only practical, too, when you have a very small total outcome. Even 36, even in the 30s, that would be a really high number, right? So let's shift gears now over to the counting principle, and let's look at some examples there. On page 644, it gives us a track example. At a track meet, there are 6 running events, 3 throwing events, and 2 relay events. If I were to do a tree diagram for this, there would be 3 categories, and then I would match them all up to find my total. However, there's another method. If I know that there are 6 possible running events, 3 throwing events, and 2 relay events, I can multiply those numbers together to find a total possible event combination for this track meet. So I just simply multiply those options together. All right, look at example 2 now. It says the standard New York license plate has 3 letters followed by 4 digits. How many different license plate options are there if the letters can be repeated? So, okay, so let's start with the letters, 3 letters. Okay, so my first letter, though, and we'll give me an example of a letter. A. B. So on that first option, how many different letters could that first letter be? 26. So, guys, this has kind of a deeper... you have to understand that although the first option is only 1 letter, there are 26 different letters that could be that first letter. Would you agree? Yes. Now, since they can be repeated, let's say my first letter is a B. Could my second letter be a B too? Yeah, because they can be repeated. So I have 26 options for my second letter too. And then my third letter is the same thing. All right, do you see where I got the 26 from? Yes. Malcolm, pay attention. Take notes. Pay attention. Okay, now let's talk about digits. How many digits are there without them repeating? 10 digits. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 digits to choose from, okay, for that first digit. So say the first digit is a 4, right? The second digit could be a 4 too. So there's 10 options for each digit, and there are 4 digits, so I multiply 10 4 times. Do you see how I did that? All right. So first 3 are letters. Well, there's 26 options for each letter. The next four are numbers, and there's 10-digit options for numbers. Multiply them all together, that gives you your total combination. Go ahead and do that. What's your total? 175,760,000. Very good, very good. Combinations for license plates. Well, that's a good thing, right? Because New York has a lot of people in their population, a lot of license plates to issue. So it's good that they have a really high combination, right? Because they can't duplicate them. So yeah, all right, so that's kind of where we're going with that. So now let's look at another example. All right, this is finding probability. And again, it comes back to I have to have a total in order to be able to calculate probability. So now you're trying to generate a password on your computer. Your password can be 4 digits. Okay? So what is the probability, though, that those 4 digits are 1, 2, 3, 4? Well, the first thing you have to do is calculate your total number of possible combinations. So again, how many digits could be in the first digit? 10. And since they can be repeated, it's 10 times 10 times 10 times 10. Do you understand why I'm repeating that? All right, because there's 10. Okay, think about it. The first digit, name me a number. 1, or what could the first digit be? 3. What could the first digit be? 6. So there's 10 possibilities of what that first digit could be. So that's why it's 10. And since the number can be repeated, there's also 10 possibilities for the second, the third, and the fourth. And when I multiply them, I see that I have 10,000 possibilities, possible combinations. But what did it want me to find? The probability that my combination is what? 1, 2, 3, 4. So remember, in parentheses, I put the probability that I'm trying to find. What is, what am I trying to measure? What is my outcome, my favorable outcome? Well, the passcode 1, 2, 3, 4. All right. So how many combinations out of 10,000 would be 1, 2, 3, 4? Just 1. That is a very unique passcode. 1 out of 10,000. All right. I want you to look at the bottom of page 645, and I want you to do numbers 1 and 2. Do numbers 1 and 2. Number 1, so there's 35 rock CDs and 12 pop CDs, so when I multiply them, I get 420 possible combinations. Did you get 420? Yes. Okay. 35 times 12.
I got 47.
What? No, don't add, don't add. That's a very common mistake. Do not add. You multiply the possibilities. Okay? Now, look at number 2. Again, so when you first look at it, you say, okay, 3 number cubes, so 3 possibilities. But how many sides are on a number cube? 6. 6 sides on a number cube. So if I do 3 number cubes, 6 times 6 times 6 is 216.
I did 3 times 3 times 3.
No, a number cube has 6 sides. 6 sides, okay? And yeah, because you see, when you first look at it, you think 3, but remember, a number cube has 6 sides. So just like you had a letter option, but there was 26 letters to choose from, you have a number cube, but there's 6 sides, so you have to multiply by 6. All right? Now, I am changing your homework for the weekend. It's actually going to be about the same number of problems, but I'm going to save you a ton of time because you only have to do 1 tree diagram now instead of an entire homework assignment where all you're doing is multiple tree diagrams. Okay? Sound fair enough? Okay? So you have 1 tree diagram, number 8. Number 9, you're finding a probability from the tree diagram. So that's just a fraction will be your answer. On 13.3, these calculations, guys, you're going to do them really quick because you're just multiplying the possible outcomes together to find your total. All right? So this is going to be your homework tonight, due on Monday. And if you understand that, that's everything you need to know for both 13.2 and 13.3.